So we have found some solutions in some cases to these constant coefficient linear differential equations, solutions of this form. Now we're going to consider a special case here. Let's consider the possibility that the characteristic polynomial in question has roots that are all real. We know that sometimes polynomials have complex roots. We're going to say, let's consider the case where that doesn't happen, all real roots, and furthermore, that they're all distinct. So let's suppose that there are no repeated factors in the characteristic polynomial. And we say that then the factors are all distinct, and correspondingly, since factors correspond to roots, we say that the roots are all distinct. Okay, so in that case, if the roots are all distinct real roots, how many solutions are we going to find? Are we going to find enough? We got lucky, it would seem, in the examples that we've done to have found exactly the right amount. Will that always be the case? Well, in general, we're going to get one solution for each root that we find of this sort. How many roots are there? Well, the number of roots of a polynomial is equal to the degree of that polynomial. This is an old fact from algebra. It's called the fundamental theorem of algebra. Nevertheless, it's something you presumably saw in an Algebra 2 class. So a cubic should have 3 roots. A quadratic should have 2 roots, etc. Again, we're talking about distinct real roots. Okay. What is the degree of the characteristic polynomial? Well, it's the order of the differential equation. By the way, we'll use this little abbreviation very often. Constant coefficient linear differential equation. It's kind of a mouthful, so it takes up a lot of space on the page, so it's just easier to write CCLD. Okay, so in particular, the way we get the characteristic polynomial is for every derivative, we write down a factor of lambda. Okay, all right. What else is equal to the order of the differential equation? Well, we saw long ago that the order of the differential equation tells you the dimension of the space of solutions. And what does the dimension of the space of solutions equal? Well, it equals the number of vectors in a basis. That's what dimension is, the number of vectors in a basis. And the way we would say that in this context is the number of functions in a fundamental set of solutions. So, okay, all of these things are equal to each other, and so in fact what we have shown here is that the number of solutions we will find of this form is equal to the number of solutions that we need to find to form a fundamental set. So in other words, in this case, where you have distinct real roots, this is it, right? These are all the solutions, and linear algebra games from there give you the complete set of solutions. Okay, now, of course, unfortunately, we can't always assume that we have distinct real roots. Sometimes they're repeated roots, sometimes they're complex roots, etc. So let's start considering these other cases. What if you have a repeated root? Now, still real. We'll worry about complex later. But what if we have a repeated root? So for example, here's a differential equation. There's its corresponding characteristic polynomial, which we want to find the roots. And note that that characteristic polynomial factors. But it factors with 2 copies of this same factor minus 1, lambda minus 1. Said differently, this root, lambda equals 1, is a root that it's sort of a root twice in some sense. We say that this root has a multiplicity of 2. Okay. So, yes, this root does still give us that solution, but unfortunately it's only one solution. So there's this awkwardness where this is a solution, this is a root twice, but it only gives us one solution. So we're out a solution. We're missing, in some sense, a solution. And you might even say, because this was a root twice, it sort of owes us, in some sense, hopeful sense. It owes us 2 solutions. It's only given us 1. I kind of feel like this root owes us another solution. So with that completely irresponsible speculation in mind, we say, hey, maybe, okay, so maybe it's something that looks kind of like e to the 1x. We already know that that's a solution, but maybe I fudge this somehow. Maybe there's something I do to it that makes it become a second solution. So let's see. Now this is again wildly irresponsible, highly speculative guessing. But let's just see what happens if I take that and I plug it into our differential equation. The differential equation turns into this, and a certain amount of algebra that I'll let y'all work out for yourselves. But if you work out this algebra, what you'll find is that you get down to this: u double prime equals 0. So in other words, if this is going to be a solution, if something of this form is a solution, that u factor has to be some, ax plus b. It has to be some linear, unfortunate use of the term, but something of the form ax plus b that would, of course, satisfy this differential equation. And x, of course, is an easy example of that, and you can actually confirm for yourself, if you take that as u of x, let u of x equal to x, then you actually do get a solution here. And that's something that you guys can confirm for yourselves. Okay. All right. So notice that the root in question had it was repeated, you might say, one time. It had a multiplicity of 2, but it was repeated one extra time beyond the one obvious time, and therefore we were supposed to get one additional solution, and therefore a grand total of 2 solutions. That was what we hoped for, and that came to pass. Okay. Fortunately, this generalizes. We're not going to prove the theorem on the next page right here. We will prove it later when we have some more powerful tools at our disposal. For the moment, we're simply going to make use of it. Here it is. Here's the theorem. I have to make a definition first. We have a polynomial that factors. I suppose this is the complete factorization of our polynomial. Roots, of course, are those numbers. This number here tells you how many times that factor is repeated in the factorization, and correspondingly we say that this is, conceptually we say that this is the sort of how many times that root is a root. We call it the multiplicity of the root. Okay. All right, well, that definition being made, here's our theorem. Suppose you have a characteristic polynomial for a CCLDE. Suppose you have a root. Of course, roots give you solutions like that. But suppose that root is has multiplicity m. The good news is that here is the complete list of solutions that you get from that root. And notice that what that complete list of solutions is you have the same e to the rx, and they've just all been tweaked, and the tweaks are always powers of x. So e to the rx, x e to the rx, x squared e to the rx, etc., and you go all the way up to x to the m minus 1 e to the rx. In doing so, notice grand total, this root, it appears m times. It therefore corresponds to m different factors. And grand total, we sort of feel like it owes us m solutions. And grand total, how many do we get? We get a grand total of m solutions. So we got all the solutions that we feel like we should get for this root.